Welcome to the HPC Best Practices webinar series, which is brought to you by the IDEAS Productivity Project funded by the Exascale Computing Project in collaboration with the United States Department of Energy, Computing Facilities at the Argonne, Oak Ridge, and Lawrence Berkeley National Laboratories. I'm Osni Marcus from the Lawrence Berkeley Lab and will be the host for today's webinar, Quantitatively Assessing Performance Portability with Roofline. The webinar will be presented by John Pennycook from Intel and Charlene Yang and Jack Deslippe from NERSC, the National Energy Research Scientific Computing Center. John is an HPC application engineer in the HPC ecosystem and applications team at Intel. He has a lot of experience in optimizing and parallelizing applications from a range of scientific domains. He has a PhD in computer science from the University of Warwick in England. Charlene is an application performance specialist at NERSC, where she focuses on performance characterization, performance optimization, performance portability. She works with code teams in the NERSC Exascale Science Application Program, and he helps developers, users to identify performance bottlenecks and also provides advice on optimization strategies. She holds a PhD degree in electrical and electronic engineering from the University of Western Australia. Jack is the application performance group lead at NERSC. He and his group work with DOE application teams to evaluate and improve the performance of applications of Cori and the future systems at NERSC as well. He also acts as a consultant to develop for material science applications on NERSC systems, and he received a PhD in physics from UC Berkeley. All attendees have been muted. We will be receiving questions through the WebEx chat and also the Google Doc. I have pasted the link to that Google Doc in the WebEx chat. The webinar will have breaks so the presenters can respond to the questions that come in. So the webinar will start with Jack, and then will be followed by John and then Charlene. So then, Charlene, I'm going to give you the share. And Jack, you can start.
Okay. Can you see my screen?
Yes.
Okay.
Okay, well, thank you, Osni, for that introduction. I have to apologize to everybody. I have a bit of a cold, so if I am coughing or if I'm hard to understand, I apologize. Let's flip ahead to the next slide. So I want to just kind of talk briefly in order to motivate the discussion around quantitatively measuring performance portability. And I'm coming from a perspective as somebody from the facility. So we're from, Charlene and I are from NERSC, which is the Mission HPC Center for the Department of Energy Office of Science. And one of the things that's sort of unique about NERSC is that more so than really any other HPC facility, probably in the world, we have a very diverse set of users, projects, code, science areas, people from different countries and states using the application. And so we kind of have a perspective of the broad scientific computing community and the diversity in that community. So let's move on to the next slide. And the challenge for us has really been how to enable NERSC's diverse community of those 7,000 users, 750 codes, to run on advanced architectures like Cori, which is a KNL architecture, and then Perlmutter GPUs and beyond, and do so productively. And this is a challenge that many other facilities face, but I think, at NERSC is one of the places where the scientific community, the kind of rubber hits the road. And as the HPC community moves towards exascale, we want to make sure that community doesn't get left behind. So as we deployed Cori a couple years ago, we realized that the challenge that the community is facing is substantial, and that the system represented our first step on the way to exascale and kind of a change in the type of systems that we had procured for, 2 decades before that. So, with our previous procurements, the users could rely on the fact that their code, with basically no modifications, would run faster on the new system, even on a node-per-node basis, than whatever the previous generation system was. And we thought that for the first time that might not be true with Cori, that there are substantial architectural changes that people kind of need to think about and wrap their heads around. So, for example, there's more parallelism in terms of the number of cores on the node. There's more parallelism within those cores about how many operations they can do every cycle. There are changes in the memory hierarchy, including an addition of a small amount of fast memory. And we thought that this was difficult enough that we kicked off a new activity to really engage users at a much deeper level than we had before. Can we move on to the next slide? And with Perlmutter, there's NERSC is continuing this progression towards exascale energy-efficient architectures. So we announced Perlmutter in the fall. It'll be the next system that will arrive at NERSC in 2020. And this system will support a hybrid architecture where there's a number of CPU-only nodes with AMD EPYC processors that we think many of the optimizations are co-teams made targeting KNL will make good use of. And then there'll additionally be some GPU-accelerated nodes where a lot of the performance of the system will ultimately lie. And this provides some additional challenges, in particular in terms of providing a path to our users that is sort of seamless as they transition from Cori to Perlmutter and beyond. Can we move to the next slide? So one of the things that we've tried to do in order to scale our support for the community, where we have over 750 apps running on our system, is to come up with a way to frame the conversation around performance and around performance portability in a productive way, that it's easy for users to understand, but it also gives kind of actionable information. And in particular, I think users are kind of need to know the following things. They need a sense of their absolute performance when optimizing applications. I've been to many presentations, and I've even given presentations myself where people will say something like, my code runs 5 times faster today than it did 3 years ago. And while that's in principle good, it really doesn't give you any sense of where you stand in an absolute sense. It's kind of meaningless in that way. And so users need to know if their performance is good. They need to know why they're not getting peak, which directions they can move in, and most importantly, probably when to stop when they've reached kind of diminishing returns. And so they need to, when you have an architecture like KNL or GPUs, there are multiple architectural features that may be limiting your performance. How do you know which potential optimization direction to apply, and what is the limiting factor in your performance? And how to improve performance portability. So users are scientists. They have accounts on many systems. They don't want to have to rewrite their code every 2 to 3 years as a new system is brought in. And so they want to think about both the portability and longevity of their application. Can we move to the next slide? So we spent a lot of time trying to frame this conversation with our users in a way that would allow this broad scientific community to move forward. And, we thought, as we were thinking about the optimization process for Cori, we thought about different ways to talk about the process, and we came up with some different analogies, like a staircase or a space elevator where you just make one change in your code, and it's just the right change to make your code just fly on the architecture, or is it so complicated you can never leave in terms of like a labyrinth. Can we go to the next slide? And the kind of cartoon analogy that we came up with was that it was like an ant farm where you're constantly kind of running this lawnmower over your code to decide what the current bottleneck is. And then there's different things that you need to do to address that. But let's go to the next slide. And really how this evolved over time was using the Roofline model, which Charlene is going to kind of introduce later and talk about how you can use that to quantitatively visualize performance portability. But this started with us visualizing just performance and the optimization process. So here is the optimization for one of our applications, the warp code. And you can see that it's that the performance of the code as plotted on the Roofline curve is moving up in terms of total performance, and also to the right in terms of arithmetic intensity or the data reuse in the application. And as we prepared applications for Cori, we produced a number of these curves, and they're very satisfying, and they're particularly satisfying to the application developers themselves because it gives them a sense of one sort of achievement. You can actually visualize your improvements, but also a sense of kind of a deeper understanding of what the bottlenecks in your application are, and ultimately an understanding of when to stop. Can we go to the next slide? So we like to do the same thing with performance portability. We want to frame the performance portability process and questions in a way that can really benefit the scientific community. So I think everybody really kind of knows roughly what performance portability is. But in order to make progress, I think it really pays to be precise and in particular quantifiable. And so here was the definition that NERSC, in collaboration with Argonne Leadership Computing Facility and Oak Ridge Leadership Computing Facility, came up with as a definition. And then really the point of the rest of the seminar is how do you go about measuring that? And so the definition is that an application is performance portable if it achieves a consistent ratio of actual time to solution to either the best known or the theoretical best time to solution on each platform, with minimal platform code required. So let's move on to the next slide. And let's talk about how you measure, how you quantify that now. And so there are many bad ways to do this, and some of these are sort of been used in practice, and that's just to compare the time to solution on one system to another. That's obviously a bad thing to do because the systems could just have completely different capabilities. So the time to solution doesn't really represent any measure of portability. Another bad way is just to compare the ratio of the actual app performance to the peak system performance. And this is not a great idea because your application performance might be limited by something that is not, the related to the max CPU frequency or the max CPU flop rate. It could be related to memory bandwidth or network bandwidth or something completely different. So we think good ways to measure performance portability are comparing time to solution on each system against some well-known optimal implementation of the algorithm. Or two, compare the performance on each system against the relevant Roofline model ceiling on each system. And Charlene's going to talk a lot about that just here in a minute. And we've included, we have instructions available for how you do that on both the KNL and the GPUs. So next slide. So I'm going to wrap up here. This might be a decent stopping point if there are any initial questions. And then John, I think, is going to take over on this slide. Is that right?
Jack, I don't see any questions so far. So
okay.
I'm gonna then transfer the screen to John. Ready, John?
Okay, it hasn't worked. Give me 1 second. Okay, is that full screen now?
Good.
Okay. So just to reiterate what Jack has already said, I think when we talk about the 3 Ps, performance, portability, and productivity at kind of a very high level, it's very easy for us to agree on what they mean and what our goals are. So performance really means we want to run fast enough to enable scientific discovery. Portability means we want to support lots of different architectures, CPUs, GPUs, FPGAs, and so on. And productivity really means that we want to minimize our effort in development and maintenance. And even when we start to combine these two of these 3 Ps to make new terms like performance, portability, it still makes sense, and we still have an idea of what we mean. Performance and productivity would enable domain scientists to write high-performance codes without spending a lot of time actually tuning those codes to get performance on one particular system. Performance portability would mean that your applications would run at all of the different facilities you care about and still have good levels of performance. And portability and productivity would enable developers to program in one shared language or programming model, so you wouldn't have to rewrite everything from scratch just because a new machine type comes along. And if we can all agree on what those goals mean, then we can probably also agree what an ideal application looks like. So ideally, our applications perform as well as possible. They run on all platforms, not just the ones that we know about today, but even the platforms that someone's going to propose in the future, so we don't have to rewrite things. And ideally, it requires very little effort or even no effort to write new features or maintain existing features. But like Jack said, I think if we just have these very high-level ideas, it's very difficult to actually assess how well we're doing as we develop our own applications. It's very difficult for us to say how close we are to those ideal applications. We can't do things like compare different efforts. So if I, as a user, need to choose between 2 different libraries, so I've got 2 different candidate libraries so I could plug into my application, and I want to pick the one that is going to improve my performance portability the most, there's no standard methodology for that. And also, like Jack was saying, we can't set a development goal and decide when to stop. You can't say, I want to stop at 80% of this ideal application without some way of measuring how close you are to that ideal. So I want to point out that we're not looking to force our terminology or the metrics that we have proposed upon anybody, but we have found them to be quite useful in guiding discussion with developers and refining what we actually mean by performance portability and what tools we need to realize our goals. We consider our work on performance portability to very much be a work in progress. So we welcome all feedback on the metric, and we're looking for collaborators to help us evaluate that metric on new applications and help us develop new tools for measuring things and analyzing the results. Okay, so here is the metric itself. We first proposed this a couple of years ago in a workshop paper and a journal paper. So that's myself and 2 of our colleagues, Jason Sewell and Victor Lee. And what the maths here really says is that the performance portability metric is the harmonic mean of an application's performance efficiency on some set of platforms H for a particular input problem. And then there's a special case where we force the performance portability of an application to 0 if it doesn't run correctly on any platform in the set. And that might seem a little harsh, but the basic idea is that you shouldn't be able to claim that your application is performance portable if you couldn't even claim that it was portable. And I'll come back to talk about what some of the other terms in these definitions and metrics mean later on. But at the bottom of this slide, you can see there are 3 example graphs here, and this is really just dummy data, so made up data to highlight how the performance portability metric works, and that we think it's actually quite intuitive. So in the case of application 1, you can see that the performance efficiency varies quite a lot with different platforms. And the performance portability metric acts as an average, but because it's the harmonic mean, it tracks the minimum performance efficiency, which is platforms B and C. So it comes out at about 23%. And if you look at application 2, where all of the performance efficiencies are the same on all of the platforms, your performance portability score is exactly the same number, it's 20%. And that's exactly what you would expect. And compared to application 1, we think that most developers would prefer application 1 because they would accept that slightly decreased performance efficiency on platforms B and C as a trade-off, so in exchange for the higher levels of performance efficiency on the other 4 platforms. And then application 3 shows something quite different again. So here we've got 5 platforms with 80% performance efficiency and a single platform with 10% performance efficiency. And again, as I said, the harmonic mean pulls things down. So the presence of platform E in the platform set means that instead of an 80% performance efficiency, performance portability, you get 37%. And this is interesting for a couple of reasons. So from a user perspective, it shows that actually computing performance portability relative to a set of platforms that you care about is actually really important. So if you knew that you needed to support platform E, then the performance portability is 37%. If you know that platform E is a platform you don't care about, it's something you're never going to buy or it's not available at your facility, then you can actually remove platform E from your platform set, recompute performance portability, and end up with a score of 80%. But as a developer, looking at all of these platforms and the resulting performance portability score might encourage you to either report that you are performance portable only across the platforms that you truly support, so you don't make misleading claims, or you decide that you want to include E in your platform set and focus your development effort there. Okay, and so the next couple of slides, I'm going to talk about some of the other terminology in the metric and definition. So when we say application, we really mean anything that can accept an input problem and produce some output. And that seems a little fuzzy and vague, but it's deliberate because we want to allow for an application to be something as simple as a shell script or a library API that actually calls out to different applications on different platforms. So as an example, consider like a BLAS library that makes calls to either MKL or cuBLAS, depending on whether it's running on an Intel CPU or an NVIDIA GPU. Well, the performance portability of that high-level library interface is higher than the performance portability of MKL or cuBLAS on their own. And the reason that we account for input problem as an input to the metric is that anytime you change the input problem, you'll be sending potentially the code down very different paths. And in extreme cases, there may even be some features of an application that haven't yet been ported or enabled on a particular platform. So any of these things could impact performance, and that could impact your performance portability. So by varying the application and problem, we can start to answer interesting questions, like which of these applications has the highest performance portability for the problem I care about. So that's how you would choose between different libraries or different software packages. You can ask whether the performance portability of your application is actually consistent across different input problems. Maybe that's something that you want to aim for. And you can also look at the impact of some code transformation on your performance portability. So this is the way that you start to be able to track performance portability over time. And then what are platforms, and what is this platform set H? Well, a platform is everything that makes up your execution environment. So that's hardware and all the software, the operating system, the compiler, all of the runtime tools, all of the compiler flags, anything that happened to be running at the same time when you actually took your performance measurement, any environment variables, thread affinities, everything. And that's because any of those things could impact performance and then impact your performance portability. But we place no restriction on what platforms can actually be used in a platform set. And that may seem a little odd because it does mean that you can compute the performance portability of a single platform. It's just the performance efficiency of that platform. And you can also look at the performance portability for sets of platforms that seem quite similar. So you don't have to compute the performance portability of across, say, CPUs and GPUs. You could look at the performance portability across a set of just CPUs. And I'll talk a bit more about that in a second. So changing the platforms, we can answer questions like, what is the performance portability of my application on the platforms that I care about, the ones that are available in this cluster or the ones available at my facility, or the facilities that I have access to. We can look at whether a given application is more performance portable across platforms of specific types. So in a previous publication, we looked at taking the performance portability across just CPUs and the performance portability across just GPUs, and then as a third set, looking at the performance portability of CPUs and GPUs. And what that highlighted was that the applications we were looking at, in some cases, had an affinity for GPUs. You can test assertions from framework developers that their framework provides a certain level of performance portability between platforms of certain types. And you can look at the performance portability of an application across things like different generations or even different SKUs of one architecture. So for example, moving from Haswell to Broadwell to Skylake. And the reason you might want to do that might not be immediately clear. But let's say you are developing a cache-oblivious algorithm. So one way that you can test that your algorithm is working, it's truly cache-oblivious and it's providing performance benefits in the manner that you expect, would be to look at the performance portability of that application when moving between CPUs with different cache sizes. Okay, and then the final term that I want to talk about is this performance efficiency. So in the paper, we talk about two different types of performance efficiency. One is architectural efficiency, and this represents how well an application utilizes each platform's resources. You can think of it as being very similar to percentage of peak or percentage of performance relative to the roofline. And then application efficiency is slightly different. It represents whether an application uses appropriate algorithms on each platform. And rather than being a ratio to theoretical peak performance, it's a ratio to the best known performance. So this is the best performance that's been demonstrated by anybody for your application or something solving the same problem on the same platform. And both of these efficiencies have shortcomings, so we actually suggest that where possible, it's best to calculate and present them both. Because, for example, if you have an architectural efficiency of 100%, that doesn't actually mean that your application can't run any faster. It simply means that you've hit some ceiling somewhere and your code is bottlenecked by something. If you could find some way to alleviate that bottleneck, either through algorithmic change, so something like switching from merge sort to radix sort, or even just doing something like cache blocking, you could find yourself running much faster, even though you were previously at 100% efficiency. And something similar can happen with application efficiency. So if you're running at 100% application efficiency, that just means that you are currently performing at the best known level of performance. People come up with new algorithms all the time, so that could change. Or it could just be that when you look at your application efficiency in conjunction with architectural efficiency, you realize that there's still some more tuning work for you to do. So we recommend that you present them both where possible. Okay, and now we've gone through what the metric means and what all of the terms mean, we can start to look at some results. So here's a case study for the Babel Stream benchmark developed at the University of Bristol. And Babel Stream is basically McAlpin's stream triad benchmark, but rewritten in several different languages and frameworks as a means of looking into performance portability, but also to enable stream triad bandwidth to be computed for lots of different platforms that McAlpin's code doesn't run on. And I should point out that this is historical data, so I've got data from 2016 and 2017. So if you were to rerun these experiments, you might get different results because of changes in configuration, security patches, things like that. But I'm not really highlighting the absolute performance here, rather the trends. So what I want to point out first is that if you look at the McAlpin, SYCL, and CUDA implementations of Babel Stream, In 2016, all 3 of those had a performance portability score of 0. And that represents that there was at least one platform in the set of platforms that Bristol tested where those implementations didn't run or didn't run correctly. In all the other cases, you can see that the performance efficiency is actually quite good, and the performance portability score comes out at about 80% for Raja Kokos and OpenMP, and 60% for OpenACC and OpenCL. And if you look behind the lines at the blue and yellow bars, then you can see the reason that those efficiencies aren't higher is that typically the GPU efficiencies are quite high, in some cases even very close to 100%, but the CPU efficiencies are low, and so the metric is being pulled down by those. And if we jump ahead to 2017, then what you can see, I think the most striking result is that the SYCL performance portability jumps from 0 to 70%, and that represents that in that time period, SYCL runtimes and compilers improved to the point that Bristol were able to run their SYCL implementation on all of the platforms tested. But if you look at Raja, Kokos, OpenMP, and OpenCL, the performance portability increased by about 10% in all 4 cases, I think. And this is because Bristol went and focused their development efforts on improving the CPU performance, doing things like making sure that the code vectorized and making sure they were using non-temporal stores where appropriate. Okay, so finally I want to talk a little bit about ways you could fool people using the metric, so ways not to use the metric, essentially. So first, we think that performance portability is a measurable property of an application, so you shouldn't use it to compare platforms or frameworks unless you have lots and lots of data from lots and lots of applications and you're taking an average or something like that. We've seen that changing the platform set can have a significant impact on the performance portability score. So comparing portability across different sets of platforms is not useful, it's meaningless, because it'd be very easy for someone to add a platform that they knew wasn't supported and force the performance portability score to 0. A performance portability score is only as good as the performance baseline that it's based on. So it would be very easy to say, well, the best known performance is my own performance, so I've got a performance portability of 100%. And that's great, but it doesn't tell you anything. Similarly, problem parameters like size or floating point precision, all of those things will impact performance. So you need to make sure that you do an apples to apples comparison, just the same as you would with any performance comparison. And then finally, because our definition of platform allows for the user to set what a platform is, it's very easy for people to make these very grand claims, like my code is performance portable across 100 platforms. And that's only impressive if those 100 platforms are not just the same architecture with slightly different SKUs and slightly different operating system versions. That data might be useful, but it may not be telling you what you think it's telling you. And I want to highlight this third point because Charlene is now going to talk about a methodology for ensuring that you pick a good performance baseline so as not to skew any performance portability metric you compute.
So John, before we move to Charlene's part, there are a couple of questions here that we could go through.
Okay.
So the first one was actually, the question came in just after Jack finished. But do you have benchmark applications that do nothing important, but have measurable tasks? Would you take that or pass it back to Jack?
I think pass that back to Jack.
Hey, Jack?
Could you read the question one more time?
Do you have benchmark applications that do nothing important, but have measurable tasks?
That do nothing important but have measurable tasks. I think that's sort of that sort of describes any benchmark suite to my in my understanding of, a benchmark is something that doesn't really compute real science, but has things that are measurable. So we use a number of micro benchmarks like Stream and LinPack and a number of MPI benchmarks to benchmark certain aspects of the system. And we also have a set of benchmark suites that we use, benchmarks that we use for procurements and that we use to consistently measure the performance on the system. Those are based on real applications. So we have like a mini DFT application, a QCD application that we use, and about 6 or 7 in total that we use to kind of benchmark systems and are used for kind of procurement and also for performance variability over time. But I have a feeling I didn't quite grasp the implication of the question.
Well, so then you'll have a chance later, Jack, to answer this, think about it and answer, before we publish it, okay? So now a question for you, John. How are these concepts, also the Roofline model, extended to include internode performance, and how do you practically address this?
Okay, that's a good question. So we haven't looked at our performance portability metric in the context of multiple nodes, really. We tend to focus on single node performance. I think in theory it should be possible to extend the definition of platform to talk about a platform being a cluster, or a platform being a certain number of nodes, for instance. So you could talk about the performance portability of an application when run at a particular scale, but it isn't something we've done. So that's really just a guess at how it could be used. We'd be very interested in trying to evaluate that if someone has a code that they're interested in working on that with us. As for Roofline, I'm not sure about that one. I think maybe Charlene has an answer about that.
Okay, Charlene, so I'm giving you now the screen, okay?
Okay. But just to follow on the last question, I think Roofline is essentially focused on node performance as well. But like John said, I think it's possible to extend that to cover multi-node applications.
You can share your screen now.
Yep. Okay. So following on what Jack and John have talked about, I'm going to focus on just one term in the metric, the architectural efficiency, and how to use Roofline to calculate this and how to make it more accurate. So there are roughly 3 messages I want to get across in the next 20 minutes or so. So first is to use empirical ceilings in the Roofline analysis. Second is to account for complex instructions like divides, exponentials, and such in the flops counting. And I'm going to show you what the difference is if you don't count it appropriately. And then with a few examples, I'm going to show you how Roofline can capture different nuances in performance analysis. And all of these is to make sure that your calculation of architectural efficiency is accurate and your performance portability score is accurate. So if anybody has never heard of Roofline, this is a 20-second intro. So when you think about performance bounds, you may be thinking about the peak flops, and that may not be true always. Here, an example would be, when your code is bandwidth bound. In that case, you'd never reach the peak flops. So what Roofline says is that you're bound by the combination of the two. So when you're in a bandwidth bound region, you're bound by the product of the peak bandwidth and the arithmetic intensity of your code on this platform. And then if you're in the compute bound region, you're bound by the peak flops. So the plot is log-log scale. It's designed in this way so that it's easier to extrapolate when you have, say, double the flops or double the bandwidth, what happens with the performance. And of course, you can have multiple bandwidth lines or peak flops lines, depending on if you're running, say, a vector code or a scalar, heavily scalar code, or if you're looking at different memory levels. So how to collect Roofline data? Here we strongly recommend people to use ERT to measure these ceilings empirically. And to get the application data, in this talk, for the experiments in this talk, I have used SDE Liquid on KNL and NVProf on NVIDIA Volta GPUs. So the raw measurements you have to collect are mainly three. First is the flops, which is the total number of floating point operations, and then the data movement in bytes, and then the runtime. And with these three data entries, we can calculate the x coordinate, y coordinate of this dot. So one is the arithmetic intensity in flops per byte, and then the gigaflops per second performance. Then with all the data collected, you could plot them up onto a single graph like this. You could use, so here I have a simple example using Python. So you could try this and then have an input file like this to plot everything up. And you could also use, GNU plot or some other tools. It's really up to you. And so starting with message one, there's a discrepancy between the empirical ceilings and the theoretical ceilings. We hear a lot about, the specifications from vendors, say 3 teraflops on a KNL or 7.8 on Volta V100, but that's probably not taking into account, say, the power constraint or some specific clock frequencies you're running at. For example, on KNL, if you're running a full AVX code, your frequency could be dropped by 200 megahertz, and the 3 teraflops marketed, that's probably not considering this frequency drop. So with ERT, you can get a more realistic sense of what the peaks should be. And here I'm showing about 10% up to 30% difference between the the empirical ceilings and the theoretical ceilings. The second message is about complex instructions. So we know that additions, multiplications are counted as one flop each, but operations like divides, exponentials, or logarithms, they are actually implemented by multiple instructions, and it's not fair to just count them as one flop. And here we're going to do some comparison. So one is the canonical way of counting the flops, and the other one is the empirical way. So the example we're going to use is the GPP kernel from Berkeley GW, which is a material science code. So in the box here is the pseudocode of GPP. You can see it's made up of a few loops nested together, and there are some reductions. What you can't see is in the compute section, there are some divides, some FMA instructions, but not all of the instructions are FMA. The data type is complex double. Why we chose GPP is because it's highly parameterizable. So you can tweak certain parameters in the kernel. For example, you can tweak this number here, NW, to change the total number of iterations in this loop. And because the total data movement is not going to change, but the flops will, and so the arithmetic intensity will change. But that's just one of the examples of the different variants of GPP. We're going to use more of the different variants of GPP, so I'm going to talk about that later. But here to just compare the different ways of counting flops. If we change NW on two different platforms, you can see that at a higher NW value, the difference can be as high as 35%, and that's not negligible. And if we look at the performance, because the data movement hasn't changed, but the flops has gone up, and so the arithmetic intensity has increased, and so has the gigaflops per second performance. So here, if you look at the different dots on two platforms, both dots, so we compiled the code with FMA and without FMA, and we compared the canonical performance, which is using the canonical flops, and the empirical performance. You can see that both performance dots have moved up and to the right. So the message here is that so you may be closer to the ceiling than you think you are, and you could also be in a different regime on Roofline. So maybe here you think, maybe on the Volta GPU, you think you're bandwidth bound, but you're probably more compute bound. So that's the second message. The third one is about the different capabilities of Roofline and how it can be used in performance analysis and performance portability analysis. So here we're going to use a few variants of GPP. First, we're going to change the value of NW in order to change the arithmetic intensity. Secondly, we're going to compile the code with FMA and then without. And last, we're going to change the memory access pattern. So I'm going to talk about that in a moment. So to do this striding, so we're going to look at strided memory access patterns. We're going to break this IG loop into two loops. So one is controlling the stride size, and the other one is, going around still picking up different elements, but at a stride. So an example is stride 2, and you can see each element is not accessing contiguous memory anymore. It's jumping 2 elements at a time. So with these 3 different variants of GPP, or 3 different benchmarks, we're going to run them on 2 different platforms, and we're going to calculate the architectural efficiency on 2 different platforms, and this is using Roofline. And then we're going to plug this number on 2 platforms into the metric that John has talked about and calculate the performance portability score. So starting with the first 2 benchmarks, as we increase NW, we can see that the arithmetic intensity is growing, so is the performance. But on both platforms, the performance seems to be capped at some point. And if we look at the FMA performance, so this is the FMA, the solid symbols. The FMA curve, when it's converged, it's very far from the FMA ceiling, whereas the no FMA curve, it's actually getting very close to the no FMA ceiling. And the reason for that is simply that we don't have enough FMA instructions in the code. So apart from the lack of FMA instructions, we're getting very close to the no FMA peak. But if we look at the converged no FMA performance, the gap between the performance and the ceiling, and the gap here, you can see that the gap on K-now is a bit bigger than on V100. And the reason is that the different instruction issue bandwidth and different instruction execution bandwidth. So on K-now, you can issue 2 instructions per cycle, and you can execute 2 instructions per cycle. On V100, you can issue 4 warps per cycle, and you can execute 1 warp. So here we're talking about double precision operations. So there are only 32 FP64 cores, so you can only execute 1 warp per cycle. And so you can see the difference between the issue bandwidth and the execution bandwidth. Apart from, well, in order to do the floating point operations, we have to have some integer operations or some memory related instructions that have to happen, and they do take up place in the pipeline. So if you have some room between the issue bandwidth and the execution bandwidth, then you're more likely, it's easier for you to achieve the no FMA ceiling. So from Roofline, you can see this subtlety between different architectures. And I guess this is, part of the message that Roofline can be very powerful in capturing this. And with these dots, we can calculate different architectural efficiencies, and then we can use the metric proposed by John and a few others at Intel to calculate a performance portability score. So you can see for the no FMA performance portability score, it's almost always above 80%. That means your performance efficiency is almost always above 80% on both platforms across different AIs, and that's understandable. And for FMA, because we don't have enough FMA instructions in the kernel at high AI values, we are, the architectural efficiency is dropping, and so is the performance portability score. So I guess the message here is that the score is effective in measuring how consistent performance efficiencies are across different platforms. And then the last one is about strided memory access patterns. And as we increase the stride size, you can see the dots are moving from the right to the left, and they're getting aligned with the HBM bandwidth. And they are moving, but they will stop at some point at a certain stride size. And that's because you're getting close to almost random memory access patterns, and that makes sense, right? So again, we calculated the different architectural efficiencies and the performance portability. So the score is going up as we increase the stride size, and that just means GPP is becoming more and more bandwidth bound very consistently on both architectures. And you might think the performance is actually dropping from here to here, but the bound is also changing. So when you calculate the architectural efficiency, you're calculating against the relevant bound, not the peak, the compute peak. So here we actually see an increase in the architectural efficiency, and so on the performance portability score as well. So with that, I'd like to summarize our talk. Jack has talked about why performance portability is important, the past attempts to define it or to quantify it, and then John talked about the metric that they have proposed, and I have shown how Roofline can be used in performance analysis, performance portability analysis. I've shown how the metric that John has proposed is very effective. And lastly, I would like to stress that it's very important to use empirical Roofline ceilings in these analyses, and it's very important to accurately count flops for instructions like divides, and also comparing performance to relevant ceilings instead of just the peak flops. So that was my talk and a few references.
Thank you, Charlene. And I have a couple of questions here for you.
Okay.
So the first one, in practice, how do you measure empirical flops and canonical flops with regard to properly accounts for divides?
Okay. So here when we talk about the canonical counting of flops, we're tweaking GPP so that it doesn't have divides. So we're replacing divides with multiplies. That doesn't make sense in a scientific research way, but it gives us the canonical flops for the whole kernel. So we still use SDE to count the total number of flops in that case.
So I think it would be good to schedule like a follow-up conversation.
I'm sorry?
No, nothing. Go ahead.
Okay. And then the empirical way is just, when GPP is in its natural state, we have a certain number of divides, and then we use SDE to count those flops. So when I mean canonical, you can count the flops by just counting, by manually counting the total number of flops, and then counting each divide as one flop.
So another question here: how far is it useful to talk about achieving roughly 100% performance portability when not using the optimal algorithm setup? The optimal algorithm or setup with respect to the strided access, for example.
So I guess the metric gives you a sense of consistency, performance consistency across different platforms, but it doesn't say, the flops, the absolute gigaflops per second for that particular application. Maybe John wants to chime in.
Yeah, so I think this is a good example of a case where having both an architectural efficiency and an application efficiency can be useful, because the architectural efficiency reflects the fact that you are bound by something. So having 100% of performance portability in terms of architectural efficiency means that you are consistently hitting the same bound across all the platforms in the set. But then looking at your application efficiency, in addition to that, would highlight the fact that the other strides achieve a higher level of performance. So looking at those two numbers, you would be able to draw that conclusion, right? If they were both 100%, then that would mean that you were bound by some bottleneck on all platforms, and you were getting the best performance possible. If one of them is 100% and the other isn't, then that imbalance gives you reason to follow up.
Final question here, Charlene. Do you have a special treatment for zero operations when computing the performance efficiency? Example, on the GPU, you are using batch DGEMM by padding all matrices, which is more than 90% zero operations, but it's still very fast, which is very close to peak bandwidth and peak performance. On the CPU, we don't have batch DGEMMs, quite far from Roofline.
So let me understand this first. Zero operations.
Well, if you'd like, you could think about it and write and answer later, because just for the sake of time here.
Okay, cool.
So let me see here. The last one here. When adding the bandwidths for level 1 and 2 caches to a Roofline model for GPUs, should we use the cumulative bandwidth of all the LU1 and 2 caches on all the multiprocessors, or just for a single multiprocessor?
Well, you can do either, but you have to consistent across all the cache levels. So on the same roofline, if you're just looking at one single multiprocessor, you probably should, measure all the data movement or all the arithmetic intensity or the bandwidth just for one particular multiprocessor. But I think it's very hard to do that. L2 is shared across all the DSMs. So I guess what I would do is to measure the cumulative data movement and everything else.
Let's see here, Charlene. I think that was the last question.
Okay.
And just for the sake of time here, so I'm showing already announcing the next webinar is going to be on the February 13th, Containers for HPC. This is going to be presented by Shane Cannon. You can already register for it. So please send us feedback about this webinar. So there is a link there, IDEAS, bit.ly, IDEAS Perfport survey. The slides and recording will be available sometime next week. Also, we'll ask the speakers, the presenters, to go through the questions and answers and create those. And there's one question that I think Charlene will think a little more about it. So if you have anything else to say, Charlene and John, otherwise, thank you very much. Thank you all for joining us. And I'm going to see you in February. Charlene and John, do you have a final?
No, I'm good.
No, nothing from me.
Yeah. Thanks for organizing.
Yeah,
sure. So thank you, everybody.